Alrighty, welcome back to operating systems. So we will have a record today because this lecture will probably be the shortest one of them all. Like I said, we are wrapping up. It's getting easier and easier. We've already done all the hard stuff. So today we are talking about page replacement. So the memory on your computer is organized into a hierarchy where there's a big trade-off between capacity and speed, also price. So the fastest thing on your computer is your CPU registers. Then there's only a fixed number of those. Below that, there's some caches on your CPU, like an L1, L2, L3, things of that nature. You don't really have to deal with, but it's basically a cache for memory, and that is your volatile memory. That's your RAM on your system. And while you probably know that there's a cache between these two things, and then there are several types of disks. So there's like non-volatile memory or NVMe disks, which are just basically fast SSDs, normal SSDs like SATA devices. Then there's hard disk drives and all types of disks. So today we'll be talking about how we can use essentially a disk as a cache for memory, because the whole goal here of your caches is to be as fast as the layer above you and have the capacity as the layer below you. So we might have, I don't know, like 32 gigs of memory in our machine, maybe 64 if we're fortunate, but through using page replacement, we can actually use the disk as a backing store for our memory, and then we can go ahead and actually use a terabyte worth of memory, even though we might physically only have a few gigabytes on our machine. And you might see at the bottom here tape drives. So tape drives are a thing still in use, but they are very, very slow. But people like Google will use them for archival data. So like it's actually very, very cheap to buy a tape. They can hold terabytes and terabytes of information very, very cheaply. But no, you've probably never seen one. I've never seen any terabyte tape drive either. But if you go to a Google data center, there's actually like some piece of hardware that will go physically find the tape, pull it out, put it in a machine to read or write to it once. It's really slow. But if you're only reading and writing data very, very, very infrequently, it is the cheapest way to actually store data. So we want to hide this whole hierarchy from the user. If you're programming, you're pretty much just using memory. Like I said, each level wants to pretend it has the speed of the layer above it and the capacity of the layer below it. So memory is used by all processes, might actually exceed the total amount of physical memory of your machine because, well, if all the programs don't actually use all that memory at the same time, we can actually maintain that illusion and use the disk to store some memory for us. So for this, we can assume the size of a page on disk is the size of a page in virtual memory, just to make things a bit easier. And the whole idea of this system is, well, if you are using a page in memory, we keep it in memory. If some page in memory is used very, very infrequently, I can just write that page to the disk and store it there until someone actually needs it, and then I can reload it from disk. And this is called swap space. You might see, if you've explored your Windows machine on your C drive, there's like a file, they call it page sys, that is like a few gigabytes large on your Windows machine. That's basically a file used to store all of the swap pages, so you can actually use more memory across your processes than physical memory on your machine. So there's a few different strategies for it. The first one's called demand paging. So you use memory as a cache for the file system. You only map memory to pages to file system blocks and then only load them into memory when they're used through the page fault handler. This is the idea we had of like M-mapping a file. So we just set up all the page tables so that when we first access the page fault handler runs, we load it from the data for the disk. If the page doesn't represent a file at all, we can just map it to that swap space. So that big file on your hard drive that's just used to send data to from memory if we need to use more space. So we'll just move it to disk if we need more physical memory, and then initially we could zero out the pages if we wanted. So for programming, your process's working set should fit in physical memory. A working set is given an amount of time. It's how many pages your process actually uses. That's called your working set. If you can't fit your working set into physical memory all the time, your process will thrash. That means it's constantly swapping pages in and out to disk, which is going to be really, really, really slow and very much hurt your performance because it's basically a cache. So we will talk about how to select which page to throw out of memory and to disk, and that is called page replacement. So if we really cared about performance nowadays too, you can just disable swap if you want, and then you don't have that problem. If all your process's working set doesn't fit in physical memory, you get an out of memory error, and then RAM's cheap enough, you go buy more RAM. So that's what people in data centers will do now since the price went down, but this is something else you can have, and it's on by default. So what we're talking about today is which page from memory to kick out and throw on disk. And there are 4 algorithms we'll go over today. The optimal algorithm, which is to replace the page that won't be used in the longest. This is primarily for analyzing our page replacement algorithm after the fact, because this has to see into the future, which isn't possible to actually implement. The next one is random, so it's just replace a random page. Turns out that actually works kind of well, but we can't really analyze that one. And then there's first in, first out, so kind of exactly like the process scheduling algorithm. So we just replace the page that came in the last, or the oldest page first. And then there's least recently used, so this is replace the page that hasn't been used in the longest time. That means I go back, look at the history, see what page isn't being used, and it's likely that I'm done using that page, so it's probably a good candidate to shove off to disk. So we'll talk about this. It's probably the one you would actually implement, but we'll get into some difficulties with that. So to evaluate all these page replacement questions, and yeah, you'll probably have one of these on the final, like the scheduling questions, they'll be fairly easy. Probably won't be one of the algorithms today, but we'll see. So we have to assume our physical memory size in order to actually do these algorithms. We'll just make it laughably small. So assume our physical memory can only hold 4 pages. And then we access the following. So these are unique numbers for pages that is greater than this. So we have pages 1, 2, 3, 4, and 5, and we access them in this order. So page 1, page 2, page 3, page 4, page 1, page 2, page 5. And for all these, we assume they're initially on disk, so we have to bring them into memory. Initially, memory doesn't have anything. So we'll use the same sequence of page accesses for all the examples during the lecture. And unlike scheduling algorithms that have a whole bunch of things we want to take into consideration, like average wait time, number of context switches, average response time, for this, it's a lot simpler. We just want the fewest number of page faults possible. So every example, we will find the number of page faults. So for optimal, this is looking ahead in the future. Again, we assume our physical memory can hold 4 pages, and how I like to have them organized is for each access, I draw a box below it, which is main memory, so I should only have 4 pages in memory at any given time. And if I write a red number, red means I have moved that page from disk into memory, so that's a page fault. So if I initially access page 1, I assume that they're all on disk, so I have to bring that into memory, so I read 1 into memory, so that's a red one, that is 1 page fault. Everyone on the same page? Yeah, my jokes are terrible. All right, so now we access page 2. It is not in memory, so we do the same thing. So there's space for another page, so we would load page 2 into memory. And then, well, this is going to be boring for the first 4 unique pages. Same for 3, same for 4. Right, now everything is full. Everyone okay? All right, now we access page 1. What happens? Is it already in memory? Yes, so we don't have to do anything. We don't have to replace anything. It is already in memory, so I just draw them all again. No red, no nothing. We haven't changed anything. Access page 2. That is also a hit, right? I just write out access 2. Nothing happens. Now I access page 5. So this is where the page replacement comes into effect. So I have to pick which of these pages, 1, 2, 3, or 4 that is currently in memory to kick out for page 5. And we are going to do the optimal thing, so we are going to look into the future and see whatever page isn't used in the longest time and kick that page out. So, should I kick out page 1? No. Why? Because, well, it's the next thing I use, right? Should I kick out page 2? No, well, I use it right after page 1. Should I kick out page 3? No, it's the one I use right after that. Should I kick out page 4? Yeah, it's the one I'm not using in the longest. We're doing the optimal thing. So here's how I would write it. So I'm kicking out page 4, so I write 1, 2, and 3. They're still in memory, and then replace 4 with a 5 and write it in red. Good? All right, so now that we did the optimal thing, if we access page 1, that's already in memory. We're good. Of course, we did the optimal thing, so we should be good. Access page 2, again, already in memory. Still good. Page 3, already in memory. We're good. Now we access page 4. What do I do? Yeah, I got to kick out something, right? So I got to kick out something for page 4. It's either 1, 2, 3, or 4, or 5. And the next thing I access is 5. So I just shouldn't kick out 5. I could kick out 1 or 2. People always hate 1, so we just kick out 1. Doesn't matter. Either one is right in this case. So I can kick out page 1 with page 4, and then when I access page 5, we're all good. So now all I have to do is count the number of page faults, which is just counting the number of red numbers. How many do I got? 6. So 6 page faults. Let's keep this in mind. This is our optimal thing to do. So everyone okay with the optimal? All right, let's do first in, first out. So same situation. Can I skip the first 4 accesses because they're boring? Okay, so 1, 2, 3, 4, boring. Access page 1, well, that's already in memory. We don't have to do anything about it. Access page 2, already in memory. Don't have to do anything about it. Access page 5. What do I kick out if I do first in, first out? 1, right? So I kick out page 1 because, well, that's the first thing I loaded into memory. So I kick out page 1 with page 5. Everyone okay? All right, was that a good thing to do? Now I access page 1. So currently not in memory, I have to kick something out. What do I kick out? Page 2. Crap. So kick out page 2. Then next page I access is page 2. That wasn't very smart of me. What do I kick out now? Page 3, right? So kick out page 3. Wow, that wasn't smart. Now I access page 3. What do I kick out? Page 4, right? That's the oldest one hanging around now. And for this FIFO, you can see you always have like this diagonal line because it's first in, first out. So you can double check yourself. Your page fault should be in a diagonal line if you want to think of it that way. So now we replaced page 4 with page 3. Now we try and access page 4. Crap, what do I kick out? Page 5. Wow, this sounds bad. Now I access page 5. What do I kick out? Page 1. Right, now it looks like that. Wow, that seemed terrible. How many page faults do I have? 10, right? So 6 optimal, 10 with this, so that seemed pretty bad. So FIFO, probably a bad idea. Yeah, 10 page faults. So let's have a little thought experiment. So if I have more memory, right? So let's say I could fit 5 pages in memory. Then I should have less page faults, right? I have more space. So like in this example, if I could fit 5 pages in memory, well, I would only have 5 page faults because I can fit everything in memory, right? So more memory, less page faults. Everyone okay? The opposite should be true, right? If I have less memory, I should have more page faults. Makes sense, right? So let's just double check it. So let's do the exact same FIFO thing with memory only holding 3 pages. So first 3 accesses are going to be boring, right? 1, 2, 3, I have to load it into memory. Then, well, now we're going to access page 4. Wow, this seems already worse, so we're probably right. So we access page 4, what do we kick out? Page 1, right? So kick out page 1, oops. Kick out page 1, and yeah, this is looking bad already. So now we access page 1, which we just kicked out. Ooh, what do we kick out for page 1? Page 2. Wow, yeah, we're probably right. This is probably going to get us more page faults. This is looking bad. Now we access page 2. What do we kick out? 3. Okay, now we access page 5. Wow, what do we kick out? 4. Now we access page 1. What do we kick out? Nothing, right? It's already in memory, so mercifully we finally had a hit. So 1 is good. Then we access page 2. Also a hit, right? We're still good. Then we access page 3. So what do we kick out? Page 1. So forms a diagonal line for FIFO. So kick out page 1. Oh, oops. Now we access page 4. What do we kick out? Page 2, right? So looks like this, and then the last time we access page 5. So that's a hit. So how many page faults do we got now? 9? Well, I had 10 before, right? I have less memory now, and now I have 9. So you all lied to me. Right? This sounds kind of weird. If I want to have less page faults, I just take out a stick of memory, and I have less memory, and then I'm good. Things go faster. So that's why Apple just charges a lot for RAM, because it actually makes the system slower. Are we all convinced of that? Okay, this is something called Belady's anomaly, and it is something that is formalized. It's only for FIFO. It says more page frames, so more memory, actually can cause more page faults. So this is an anomaly only with FIFO algorithm, doesn't exist for least recently used or any like stack-based algorithms. The more memory you have, the less page faults you have. This is only a problem for FIFO, which is why it's a very bad idea for page faults. So if you like math and Greek letters and things of that nature, some mathy people prove that it was unbounded, aka you could construct an arbitrary sequence to get an arbitrary page fault ratio of whatever you want. So you can actually construct any sequence to get any page fault ratio you want. But don't worry, this is only for FIFO. You don't have to understand why, just know that this anomaly exists, and it is only for FIFO algorithms. For any normal algorithm, the more page frames you have, aka the more memory you have a decrease in the number of page faults. So, little fun thing. All right, so let's do a least recently used example using FIFO to break ties. Ties won't exist in this because I'm assuming a single core, so don't worry about it. And on the exam, I won't try and do this with multiple processes or anything like that. So we'll go back, say we have 4 pages again, and this time we will do least recently used, so we look back in the past. So first 6 accesses are going to be the same old boring thing, right? So 1, not in memory, have to load it in. 2, not in memory, load it in. 3, not in memory, load it in. 4, not in memory, load it in. Then access 1, it's already in memory. Access 2, already in memory. Now this is the first interesting one. We access page 5, and we have to figure out which one of these 4 to replace. 1, 2, 3, or 4. So if we use least recently used, we look back in the past and see which one hasn't been used in the longest time. So between 1, 2, 3, and 4, at this point, what hasn't been used in the longest time? 3, right? Everyone see 3? So it's not 2 because we just used it. It's not 1 since we just used it before that. It's not 4, so we only have 1 left. That's the least recently used one. So we replace the 3 with 5. So now it looks like this. Now we access page 1. Well, this is certainly looking better. It's already in memory, so we're good. Access page 2, already in memory, so we're good. Now we access page 3, so now we need to pick something to replace. What am I going to replace? 4. I see a 4 up there. 4, right? So between 1, 2, 5, and 4, I'm not going to replace 2. If I look back, not going to replace 1. Not going to replace 5, so I only have 1 victim left, and it's 4. So I'm going to replace 4 with 3. Now I access page 4. Turns out that was a bad idea. What am I going to replace now? 1 or 5? I see a 1. So let's look back. Not going to replace 3. I just used it. Not going to replace 2. Not going to replace 1, so I'm going to replace 5. So it turns out that is also a bad call. So now I have to pick something between these 4 to get rid of 4, 5. It's not going to be 4, not going to be 3, not going to be 2, because those are the other 3 recently used pages. So it's going to be 1, so it's going to look like this. So now we count our page faults. How many page faults we got? 8. So not quite optimal. Definitely better than FIFO, which is good. So this is something that you would hope, and you can actually implement this. So this is something you would probably want to use, although there's a few issues with it. So if you try to implement this in hardware, it's quite slow. So for the replacement, it basically has to search all of the pages in memory. You could keep like a counter or a timestamp for each page when it was last accessed. Then each time you reference that page, you update the timer on that page because, well, now you've used it recently. And then for replacement, it would have to be like an ON algorithm. You have to scan through every page, figure out whichever one has the lowest timestamp, so whatever hasn't been used in the longest time, and then you can get rid of that page. So that is really slow. We don't want to have an ON algorithm running every time we need to do page replacement. We want it to be as quick as possible. So anyone think of how we could implement this quicker? Hint, you like doubly linked lists, don't you? So could I do this in 01? Yeah. Make a linked list. And how would what would I do every time I reference a page, and how would the replacement work?
You ensure that every time you use, you have a new page, you insert it at the tail.
Okay.
And then pop the
Okay, so I could set it up that every time I reference a page, I put it at the end. and then whenever I need to replace a page, I take it from the front. And if every time I update it, it goes to the end, I have my more recently used things on this side, my oldest thing on this side, so it's just 01, right? Well, turns out that is also bad to implement. So I could implement it like this. Computer science-y tells you that's probably a good thing to do, but for each page reference, that's every time you are accessing memory. So you want that to be as quick as possible. So if for each page reference I'm moving it, in this case I'm having recently things at the front of the list, least recently used at the back, but as long as you're consistent, it doesn't matter. But for each page reference, if I count the number of constant operations I need to actually remove an element from an arbitrary place in a list and place it at the front or the back, doesn't matter, then that would require 6 pointer updates for whenever I access a single byte on a page. So suddenly I would make things much slower. So also with multiple processes, I would have to make sure that, hey, everything is synchronized. It has a mutex, so there would be contention, and it would get even worse the more processors we have. So this is also not a thing I can implement because, well, I want this operation whenever I reference something to be as quick as possible. Yeah?
Just wondering, what are the 6 pointer updates?
6 pointer updates, if it's a doubly linked list, it would have to be like, I have to look at my previous next pointer, point it to the next previous one, and then the next previous points to my previous, and then I take me, and then I put it at the front of the list. That updates that one next to me and my previous to it, and then the head of the list has to point to me now, right? So can be up to 6 pointer updates if it's a doubly linked list. So, too expensive. So what we're going to actually implement in the next lecture, because it's going to take pretty much the whole lecture time, it won't fit in this one, which is why this one is much shorter. We're going to try to implement an approximation of least recently used. And this is okay because LRU is basically an approximation of the optimal case. So an approximation of an approximation, good enough as long as we can implement it quickly. So there's lots of different tweaks we can do to implement it more efficiently. We will specifically be looking at something called the clock algorithm in the next lecture. Hint, you probably want to pay attention to that one because it probably will be on the final. Should be fairly straightforward, like a scheduling question. But there's also different things we could do least frequently used, which is a little tweak that doesn't really care about exactly how recently it was used. There is a 2Q in hardware and adaptive replacement cache, but we'll ignore them for now. We'll settle on exploring the clock algorithm. So, page algorithms, they aim to reduce page faults. We saw the following: optimal, which is good for comparison, not realistic because we have to go into the future. Random actually works surprisingly well, works better than FIFO. FIFO, it's easy to implement, but it has that weird Belady's anomaly where, well, if we have fewer or less memory, we have fewer page faults. Doesn't really make sense. Then we saw least recently used. It gets close to optimal. We could implement it, but it's expensive to implement, and we'll get into what we would actually use in the next lecture. So, sweet, we have 20 minutes left. So just remember, pulling for you, we're all in this together.